Okay, so the next piece of electronic equipment we'd like to do, just using AND gates and OR gates, but now the size of the gates might get bigger than 2 inputs, would be, suppose we wanted to have a piece of electronic we build like this. Okay, and then we have inputs coming in. Let's do it this way. Suppose we have 2 inputs coming in. Okay, so this is a piece of hardware we're creating, and then we have okay, so let me just describe what this thing is doing. We have the ability now, we can put a number here. With these 2 bits, we could put numbers between 0 and 3, right? 0, 1, 2, and 3. If, for example, we put a 0 here, a 0 and a 0, what will happen? No electricity will flow through these red lines, which means coming into this first gate, if you remember from last week, we said anywhere we put a little 0, that means there's a NOT gate is implied. So by having both of these 2 numbers set to 0, no electricity, that means no electricity flows into these NOT gates, which means that electricity does flow into this AND gate. Right? And with a 0 and a 0 here, because I have every combination, so this really represents whatever number we put down here between 0 and 3 is going to cause one and only one of these 3 AND gates to turn on. The other 3 will have to be shut off, right? Because these are 3 input AND gates. And I'll be guaranteed, whatever number I put here, I'll be guaranteed that at least one of the lines coming in will be off for 3 of them. And the 4th one may or may not have output coming out. Does that make sense? So, for example, if I put a 0 and a 0 here, I'm going to have a 0. I'm going to have a 1 and a 1 coming in here, because the 2 zeros will be flipped. And I'm going to have a 1 and a 0 here, and I'm going to have a 0 and a 1 here, and I'm going to have a 0 and a 0 here. Right? So with the number I apply here, will determine which one and only one of these could possibly have current come out. 3 of them will definitely have no current coming out, no electricity coming out. And one of them may, what would have to happen for a current to come out of it? The green line would have to be on too, right? So, what will the output of this thing be? If you had to describe it in English, what would it be? There's going to, you're going to say, depending on what this number is, and if the green line is on, something along those lines. So this is either going to be a 0 or a 1. So this gate has pretty complicated input. It has four bits coming from something, and then 2 more bits kind of telling us which one of the 4 bits we should care about, and disregard the other 3. And what would the results end up being? So if you had to describe it in English, it would be like this. The 2 bits down here will give us a number between 0 and 3. We'll call this the 0 gate, the 1 gate, the 2 gate, and the 3 gate. And I can put a number down here between 0 and 3, and that'll tell me to shut off all the gates with the exception of whatever number I put here. All the gates will automatically shut off. So I'm guaranteed, if I put a 0 here, I'm guaranteed the output of this is a 0, the output of this is 0, and the output of this is a 0. But, because I have a 0 here, these 2 are on. What is the output of this line? What? Well, not 1, but whatever this green line was. Okay. So, suppose the green was 1, 0, 0, 1, and I set this to 0, 0. What will happen? This one will come out the other end. So what is this device really doing? I'm basically saying, out of these 4 fields, I care about one of them and want to disregard the other 3. And the one I tell you I care about, that's what I want to come out. If this was a 0, then the output of this circuit would be 0. So really, with this number, I'm telling you which one of these 4 I'm interested in. So I'm basically transferring its number out of this gate. And this is how we're going to address memory. So, for example, if you have a line of code, C equals A plus B, the computer is actually going to do several steps. It's going to get the value of A, store it somewhere. Then in a separate step, it's going to get the value of B, store that somewhere else. Then in the third step, it's going to take those 2 copies, and with electronic components we'll talk about next class, we'll add the 2 numbers together, store that result in a third place, and then we're going to take that result and store it back into memory location C. But with this type of electronics, we can decide, if these were our 4 memory locations, I can, with these 2 controllers, can tell you which one I want to get a copy of. I'll say ignore all the other pieces of memory. There's 4 pieces of memory. I could say ignore 3 of them, but there's one I'm interested in, for example, A. So I could say to my computer, my processor can say to the memory, send every piece of, well, cancel out every piece of memory in my whole system, but only send me the contents of a particular piece of memory, the one I care about. So it'd be a piece of electronics like this, but just much, much larger. Okay, and this is, for those of you who took whatever that electronics class, does this thing have a name? Is it the demultiplexer? Does that ring a bell? I don't even know if they name these things anymore, but it's this piece of equipment where you can give what address you care about and have all the other ones canceled was generally called a demultiplexer. Okay. Okay, now, another piece of equipment we'll need for addressing memory Okay. So another piece of equipment would go like this. I'm drawing, the notes have examples where there's 8 pieces, and I'm doing ones with 4 pieces, so they're half the size, so that's simpler to follow. But so again, we're going to line up 4 AND gates. And then we're going to have the input go 0, 0, 0, 1, 1, 0, and 1, 1. We're going to have 2 inputs. And each of the inputs get wired into the AND gate. Okay. Now this uses some similar logic to the piece we did before, but if you wanted to describe in English what's happening. So generally I draw the inputs on the left side and the outputs on the right side. So this has 2 inputs and 4 outputs. Now I can put a number like this. I could put the number 0, 1, meaning no electricity here and electricity here. And what would the result be? Sometimes it's good to just try a few examples and then you kind of figure out what's happening. A 0 here means a 0 here, but this gets flipped to a 1 with this not here. So we have a 1, and this 1 would be a 0. So this, and it's an AND gate, so nothing comes out. This 0 gets flipped and becomes a 1. This 1 stays a 1, and electricity comes out. This 0 becomes a 0, stays a 0. This 1 becomes a 0, and no electricity comes out. This 0 becomes a 0. This 1 stays a 1, and no electricity comes out. So if you were to describe in English, what is this thing doing? If you tried all the other 3 combinations, you'd get it, but do you see the pattern of what it's doing? We can, with these 2 inputs, there's 4 combinations, 0, 1, 2, and 3 in binary. And each time we're going to get a different result. What would the results be? How are they connected back to the binary input?
It's converting binary to whatever. So it'd be, if it's 0, 0 is there, you would get 1, 0, 0, 0, would be 0, 8.
It's converting to decimal?
It's converting, well, whatever value.
Well, it goes 0, 1, 2, 3.
Yeah, so like, so just for another example, suppose we put the number 2 here. So this is like the higher bit and the lower bit. If we put a 2 here, then this would be 0. Actually, everything would change.
Yeah,
Everything would be the output.
the third one down would be the output.
And then
This would be a 0. These would flip. And these would flip 1 and a 0. And this one would become on. So when we put in a 1 as input over here, out of 0, 1, 2, and 3, line 0, 1, 2, and 3, line 1 turned on and all the other ones turned off. When we put a 2 here, line 2 turned on and all the other ones turned off. So basically, we can put a number here, a binary number, between 0 and 3. And out of our 4 lines, number 0 or 3, that one, and only that one, will turn on. The other 3 will be off. And this thing is called a, does this have a name in your electronics class?
Decoder.
Decoder, okay. Just want to make sure these are names from a long time ago, so this is a decoder. So now, going forward, we could draw something like this. And you'll know what's inside the box is this. And what's inside this would be those resistors and transistors, right? So we're just basically taking the not piece of electronics, the NAND and the NOR, and we're just building them and just making bigger boxes of stuff that we could use. Okay, and hopefully, I usually don't like to memorize names. Hopefully you can just kind of guess. If you see 2 inputs and 4 outputs, what else could you do besides give a binary number and then have that thing turn on or off? So hopefully, I don't like doing memorizing. Hopefully it'll just be intuitive when you see something like that. You kind of remember what's on the inside. Okay. Now, I think last class we talked about a piece of electronic that we could make that had a property, and you could look back on what we talked about last class for the inside of it, but we had a box, everything ends up being a box now, that had one output and 2 inputs. And we call this thing a flip-flop. Because if you remember on the inside, it was I think it was 2 OR gates, and its output, the output of one OR gate was fed as input into another one, and the other one's output was fed back into the first one. So you could put electricity on one, and it will cause no electricity to come to the other one, which then could then cause electricity to come back to the first one. And so they call these flip-flops. Whenever you take AND gates and OR gates and feed the output of one into another and form a loop, they generally call the piece of electronic a flip-flop. So we wired one up last class that had this property. If we set, it was something like this, if we set a 1 here and a 0 here, the result would be a 1 coming out of here. We put a 1 here, a 0 here, we allow a little time to go through, and a 1 will come out. If we put a 0 here and a 1 here, that would make a 0 come out. So between using a 1 and a 0 or a 0 and a 1, we can control what comes out of here. Wiring something up like that up is not too hard to do. But the thing we made last week was interesting because if we then, after setting this to a value we'd like to set it to, if we made both of these zeros, you remember what happened?
It frozen on whatever you had last.
Right, whatever you set it to, it now stays there. And I think if we put a 1 and a 1, I think the results would be unpredictable. But we would never do that. This piece of hardware we're going to do, it's going to have one purpose. The purpose will be to set a value, and then by putting 2 zeros on it, we lock that value. Okay, now if we just did something like this, if we took the thing we talked about last class and did the following. If we put 2 AND gates in front of it, and we had 1 line this could kind of be considered a open slash lock, and this could be the value. Does that kind of make sense? What we want to do is we want to create a piece of electronic that, again, now this has, we're taking the thing we made last class, and we're just putting something in front of it. We're saying, if we put a 1 here, the 1s get fed into both of these AND gates, which means whatever's coming out of value will go into here. And if we set this guy to 0, that means we've zeroed out both of these AND gates, which means we've zeroed out this whole thing, which means we are in the remember phase. So if we put, in other words, if we put a 0 here, that means freeze this thing on whatever value it was. But if we put a 1 here, that means I'm opening the door for the value of this to be set to this value. So it's kind of like, this is kind of a door that we're opening and closing. We can open the door and you can set the field, and then we close the door. And this is the way memory is going to work. This is the way electronic memory is going to work. We're going to want to, when we do our C equals A plus B, when we're finally done, we're going to want to take the results of C and open the door to a memory location, store the number, and then close the door. So the value will be remembered later. So does it make sense we could just put this little hardware in front of the thing we talked about last class? I think it was a JK flip-flop last class, was the name of what we talked about. And now we can just put these electronics in front of this, and now we can open the door to record a number into it, and then we can close the door to make it remember its value. This whole thing this whole box is called a D flip-flop. And this is what we're going to be using as memory cells. This is all the electronics needed just to have a 1 bit of memory. So if we wanted to set this field, this is our memory cell. If we wanted to set it to a 1, we would have to open the door by putting a 1 here, and then set it to a 1, allow the current to flow through, which eventually a 1 will start coming out of here, and then set this to a 0, and we really don't care what this is. What's up here will now be disregarded. The 1 will be remembered. And as long as this stays a 0, it will stay that value. Okay? Now suppose we had a series of these next to each other. Suppose we had another one of these coming out and another one of these coming out. Suppose our computer has lots of memory. And at some point in time, we want to capture one of the values of our memory. Not all of them, just one of them. We could use the, not the decoder, the demultiplexer to decide which one of these 4 values we're interested in. We could wire that, demultiplexer in front of these to tell us which one of these 4 we would like to capture, and have all the remaining ones be ignored. So if this was our whole memory, no computer would be this small, but suppose our whole memory was 4 bits. We could write to any one of the 4 bits, whatever value we want, and if at a later time we decided we wanted to read from one of our memory locations, we can put a number on that demultiplexer, and the value of that particular memory location is the one that will come to us, and all the other ones will be ignored. Okay? Okay. So now what we're going to do is just create memory board for a computer that has 4 3-bit memory locations. So this is obviously very unrealistic to be this small, but what we can do is we can have 12 of these. We could have 12 of these D flip-flops that we talked about. So these are D flip-flops. So these are all D flip-flops. And then we're going to have a decoder, a 2-bit decoder. So the decoder says we have 2 inputs. We could apply any number, any binary number from 0 to 3. And as a result, one and only one of these 4 lines will have electricity come out of it. If we then run those into an AND gate, oh, I'm sorry, the AND gates are inside here. Okay. If we then take this input, we can decide and run this into the D flip-flops. All right, same thing here. Remember that these inputs on these D flip-flops, the lower input, if you turn it on a 1, that allows you to write into the cell, and if you turn it to 0, it locks it, it remembers its value. So these are all D flip-flops. And what we're doing is we're going to, whatever number we put here is going to cause, so let me just explain something. This row is considered a, you know how like 8 bits together is a byte? And what else is that? 16 bits is something. 32 bits is a word. Is 16 bits something? A nibble or something?
Well, 16 bits is usually a word, and 32 is a double word.
It depends on the platform at that point.
What's that?
It depends on the platform.
Okay. But so in this case, this is unrealistic. I just want something that can fit on the whiteboard. So our memory locations in this case are 3 bits each. So obviously 3 bits doesn't have a name. So we could call it a nibble, you know, I don't know, 3-bit nibble or something like that. But what that means is when we access it, we grab them all at once. So like on a real processor, they might have 32-bit addressing. So then when you say, I want the contents of a memory location, you get all 32 bits together. In this case, I'm just asking for 3 bits. So this decoder is my way of saying, I want, let's say, the 0, 1, 2, the number 2 row. So the way I do that is I would put a 2 here. And that will cause the electricity of line 2 will have electricity and all the others won't. So I can go like this. And this is my way of saying which of the 4 memory sets I want to open to accept input. And I want the other 3 to stay whatever value they were. Just remember what you were. So, I can now determine which one of these 4 rows I want to open the door to write input in. Now we got to get some input to go in, if I do choose to open the door. And the input, that should be pretty straightforward. Let's say here's our input number. And again, it's 3 bits, which is, you'll never see a 3-bit word or nibble or whatever, because it doesn't make sense to do, but it helps in this picture. Let's say this is the low order bit. Yeah. This is our input. I'm going to wire this into every flip-flop. The second bit that's coming in, I'm going to wire into the second row. And the third bit goes into the first row. This will be the high order bit. So I'm now in a position to do what? I could do something like this. I could say, I have my memory, right? I have 4 3-bit memory cells. And I can decide right now that I would like to store 1, 0, 1, 0, 1. If I apply that electricity to here and here, what's going to happen? What's going to happen is, this is a 2 out of 0, 1, 2, and 3. This is a 2. That means only electricity will come out of this line. This line will have electricity. And all the other green lines will not have electricity. So the green lines have no electricity, which means whatever value they had before will stay. Whatever it was before will stay. But I did apply electricity along line number 2, which then opened, because this is now a D flip-flop, this opens that memory location for input. And let's say I decided I want to write the number 5, which is 0, 1, 0 in binary, into memory location 2, which is these 3 cells. All I have to do is put a 2 here and a 5 here, wait a little time, and the result will be all of these boxes stayed the same, but this box became 1, 0, 1. So I now, with just wiring these electronics together, I'm in a position to pick a memory location, this location, and store this number into this location and leave everything else alone. So this concept is called addressing memory. You can address which piece of memory you want, and then you can write to the memory. Okay, now, I was hoping I have a different color marker. I have a brown one. Okay. Suppose, does this make sense so far? Right? So this really, addressing memory, there's really 2 inputs, obviously. The number you want to assign to something, and where you want to assign it. So we have our C equals A plus B. This is actually going to turn into 4 or 5 steps we're going to have to do, and one of the steps is the final step. Where we finished calculating the value of C, we decided, let's say, these memory cells map to C. We want to write the result to C, so we would have to put C's memory location here, and the results of our computation would go here, and then we just let a little time go by and it'll be there. We probably want another piece of hardware that would zero out all our memory so that way our memory could freeze, because it looks like right now there's always one piece of memory that's open and subject to change. We wouldn't want that. Okay, now one of the earlier steps of this computation we kind of discussed how we would, once we figure out what C is, we could write its result back to memory. But how could we get the contents of A so that we could then perform the computation? So let's say hypothetically the compiler decided that this piece of memory, the second one was C, this was B, and maybe this one's A. Because the compiler can pick our memory and assign any chunk of memory to whatever letter we want. We don't have control of whatever. Suppose we decided we want to capture the value of A. I want to get the value of A, then I want to get the value of B, then once I have those two values I want to add them together, and now we just talked about how to write the result back to C. But if I wanted to get the value of A, how could I do that? So let's say I had a series of more D flip-flops. Let's say I had 3 of them out here. These are D flip-flops. And all I want to do right now is I want to take the contents of A, these 3 bits, and I want to write them to these 3 bits. But I don't want this other memory interfering with it. All I care about is A. I want to get A to be copied here. I'm going to need that because I'm going to take A, I'm going to take B, and then I'm going to add them together. But step 1, how do I get A? Any idea? We kind of talked about it a little while before. If there are, I'll only draw it on for these ones. I would like the value of this piece of memory to show up here. And I would like this output to show up here, and this output to show up here. Okay, one way would be to wire it together like that. But what I'd like to be able to do is say, I want this piece of memory, not this, not this, not this. I just care about this one. What we could do is if we wired, let me just erase this. I'm just going to do the outer one, and then you can just imagine that for the inner ones it's the same thing. Suppose the output of this D flip-flop, and this D flip-flop, and this D flip-flop, and this D flip-flop could all be brought together and into something, and then I would like to be able to say, see, so this is the low order bit of the 4 different memory locations. What I'd like to be able to say is I only want this one to get copied here. Ignore these 3. Just whatever the value of this one is, have it copied there. How could I do that? One of the things we talked about before does that. What's the thing called again? The demultiplexer. Which had, remember what a demultiplexer was? So the decoder, just a little review, the decoder we set a number and it causes one of those lines to have electricity and the other one to be out. A demultiplexer, we put a number on here and it tells us out of all the inputs, only allow one of them to pass through. Zero out all the other ones and just allow the one we care about to pass through. Right? That's what the demultiplexer is. So I could put a number here like 0, 0. If I put a 0, 0 here, and the low order bits of all our memory bytes, or nibbles, or whatever you want to call these things, if the low order bits are all wired into this demultiplexer, then I could say, well, shut this one off, shut this, 0, 0, 0, this is a big OR gate. And whatever the value of this one is, will pass through because I set it to 0. So that means I care about this one not this, not this, and not this. And whatever the value of this one is will just get copied here. So if this was a 1, then a 1 would come down. If this was a 0 would come down. And if we did the same thing, a multiplexer for each one of these rows, and wired them into this 3-bit collection, I'm going to call this a register. We're going to say anytime we take bit memory, these D flip-flops, and line them up next to each other, the collection of them is going to be called a register. So what we could do is we could have this register open up, set the demultiplexer to the memory location we care about, and have its contents, and only its contents, flow into this register. So, if we decided, let's say hypothetically, I'm going to put numbers, 0s and 1s on all of these flip-flops. Okay, so suppose we wrote a line of code C equals A plus B, and our compiler will actually turn this line into something along the lines of load A into register 3, load B into register 5, add register 3 to register 5 and store the result in register 8. I'm just making up numbers for registers, and then store register 8 back into location C. So if you write a line like this in Java or C++ and compile it, it'll turn into something like this. These are the 4 steps your processor will have to follow to perform this computation. So if we had values like, so now the compiler will assign whatever variable names you're using, the compiler will assign that name to memory locations. So let's say the compiler did this. It assigned A to this row, C to this row, and B to this row. If you had values like 0, 1, 0, A is 2, and C, it doesn't matter what C is, and B is 4. And C could be anything. C could be, let's say, 1, 1, 0. It doesn't matter what 4 is. And this could be anything, whatever it was before. Maybe it was zeros from before. What you're going to have the processor do, the processor is going to take this one line, C equals A plus B, and it's really going to turn it into 4 steps. The first step will be to load. Now, another thing we're going to do is for every register the processor decides to have, you could have 32 registers, 64 registers. We're going to do this a number of times. This stuff that's in brown, we're going to do this a number of times. For as many locations as we want to store temporary variables. So our first step would be to put 0, 0 on this multiplexer and have the value of A flow to a register. The next step would be to put the value 1, 1 to get the contents of this to flow into a different register. Let's say what we're calling register 5. Then a third step, which we'll talk about next class, is now that if you have 2 numbers, how do you add them together? So we're going to come up with some electronic components for adding 2 electronic numbers together. We'll talk about that next class. So then the third step will be to add them together and move the results into a third register. And then the fourth step would be to write the result of one of your registers. So the register's flow will come into here, and then we would set this to 1, 0 to open up these inputs and store the result. So when we're finally done, 4 plus 2 would equal 6. We would end up like this. That's a 6. Right? 4 plus 2 is 6. So what our hope is, if we had a 2 here and a 4 here, and somebody ran this line, it would actually break into 4 steps. When the 4 steps are done, we want to have a 1, 1, 0 here. So So like I said, we'll talk about how to add two numbers together electronically, how you would take this number and come up with 6. We'll talk about that next class. But the steps for doing a computation like this involve reading from memory. So we'd be using a demultiplexer to capture one particular memory word or byte or whatever you want to call these into a register. Then do that again with a different multiplexer and a different register. Electronically perform the mathematical step, add the numbers together. And then once that's done, write the result back to a memory location. Okay, so did you guys, in your electronics class, did you read and write from memory? In your, what was the name of the class again? The lab?
The embedded systems? Is that the one?
Oh, like a digital, there's
The stuff was all computer architecture class.
okay. So in the electronics lab, you weren't reading and writing from memory? I thought there was a class where you create a memory